In this video lesson, we're going to focus on force diagrams. We're going to focus on how do you draw them and what they are and how to make use of them. First of all, I want to say that a force diagram can also be referred to as what's called a free body diagram. I will refer to them as force diagrams, but just so you're aware that there are also called free body diagrams. So if a worksheet or a book or a homework ever asks you to do a free body diagram, know that they are the same thing. Now, what are they defined as? Well, force diagrams or free body diagrams are basically using vectors to represent all the forces that are acting on your system or your object. There's a couple rules to keep in mind when you are drawing a force diagram or a free body diagram. The first rule to keep in mind is that the system is going to be represented with a dot. So if your system is a car, we're going to represent it with a dot. If your system is a box, a person, anything, we're always going to represent it with a dot for simplicity's sake. Rule number 2, first of all, draw any field forces that are acting on the object. Remember, these are forces that are acting on the object without touching it. In this first semester, we're really going to primarily focus on gravity as the only field force. Later on, however, magnetic and electrical forces can come into play. Rule number 3, after you've drawn in your field force, I need you to draw in the contact forces. Always ask yourself, what is touching the object? If it's not touching the object, then it is not a contact force, and do not draw it in. Now, if you get diagonal forces, a force that has x and y component, you need to make sure that you separate the diagonal force into its x and y components. Remember, this is vector resolution, and we learned about that earlier in the vector video. Finally, rule number 4, vector arrows need to point away from the dot, not towards it. So, for example, if my object was a box, and I was pushing the box, I would want to make sure that when I draw my box as a dot, I don't draw the arrow going into the dot. I draw the arrow going out of the dot, like that. Alright, let's go ahead and look at some examples and draw some force diagrams. First situation right here, a box is sitting on a table, so it's at rest. That tells me in my mind it's at equilibrium, so it's going to be some of the forces equaling 0. Now, when you draw a force diagram, you always want to imagine that there is an XY coordinate grid like shown. You do not need to draw the XY coordinate, but just imagine that it's there. In the examples that I do, I'm going to show the coordinate grid, but you do not have to draw it. All you have to draw is the dot and then the vectors pointing from it. So my box is represented as a dot, and so the first rule that I'm going to do after drawing a dot is I'm going to draw in my field forces. The only field forces that are ever going to be acting is force gravity. And remember, the direction of force gravity always points down towards Earth. So that is my field force of force gravity. Now, ask yourself, what is touching the box? The only thing that's touching the box is the table. Well, what kind of force does the table exert? Since it's a flat surface, the force that the table is going to exert is force normal. And remember, force normal always points perpendicular and away from the surface. So in other words, it's going to point straight up. Now, since the box is in equilibrium, I know that these forces have to be equal to each other since they're the only two forces that are there. So, the final thing is I now need to look at my x and y, and I need to write out what is the equation of the lines. So, in the x direction, there are no forces. So I'm going to put non-applicable, because notice, there's no forces anywhere in the x direction. However, in the y direction, there are forces. There's 2 of them. So I would say the sum of the forces is equal to force normal plus force gravity. And when I add those 2 together, they should come out to be 0. And the reason why you're adding them is because you're showing vector addition. But keep in mind, since they're in opposite direction, one of them would be positive and one of them would be negative. And that's why they would come out to be 0. Let's look at another example. Now I'm holding a box pressed up against a wall. Alright, first thing, we draw our box as a dot, which is already shown. Then I'm going to draw in my field forces. Force gravity goes facing down. Now, what is touching the box? Well, first thing I notice is that the hand is pushing the box against the wall. So in other words, it is going out to the left. Now, what would we call that force? That's a general force. We wouldn't say force hand, so we're just going to call it a force applied, or just force sub A. All right, what else is touching the box? Well, the wall is touching the box, and remember, the wall is going to exert a normal force that's perpendicular away from the surface. So in other words, it's going to look like this. Now, the box is in equilibrium in the x direction. It's not accelerating into the wall, it's not accelerating out towards the hand. So force applied and force normal must be equal. Now, if we leave it like this is saying that there is an unbalanced force in the y direction. Notice in the y direction, there's only force gravity. So if there's only one force in the y direction, the object is unbalanced, and therefore it should be speeding up or accelerating downward. But it's not. It says the box is being pressed up against a wall. So there must be some other force going up that would balance out the force gravity. What do you think that force would be? The answer is it's force friction. There is a frictional force that is being experienced between the box and the wall. Finally, we know that those two are equal because the object, or the box, is just being pressed and held there. It's not going up or down. All right, so let's go ahead and write the sum of the forces. The sum of the forces in the x direction is the force applied plus the force normal. And since it's not accelerating in the x direction, it must be in equilibrium. For the y, the sum of the forces in the y direction is force friction plus force gravity. And those two together must also equal 0, because the object is in equilibrium. Specifically, it's at rest. All right, now let's go ahead and look at an example that involves some angles. We have a box that's being pulled along the floor at a constant speed by a rope 20 degrees above the horizontal. Key thing that I want you to notice, first of all, is that it's at a constant speed. So what that tells me is that sum of the forces must equal 0. Okay, so let's go ahead and draw our force diagram here. First of all, force gravity needs to be drawn in first. That's your field force. Now, ask yourself, what is touching the box? Well, the first thing is that the floor, or the ground, is going to be exerting a force normal that's facing up. But we also have this rope that's touching the box, and it's pulling at an angle. So at the same direction is going to be your force tension. And notice it says it's being pulled at 20 degrees above the horizontal. So what that means is, imagine that there is a horizontal right here, and that's the 20 degrees. Now, notice that it's a diagonal force. This is our first example where we have to deal with diagonal forces. They need to be split into their x component and their y component. So I'm going to call this force tension y, and I'm going to call this part force tension x, and that angle is 20 degrees. Finally, notice what's going on here. You've got forces in the y that are balancing each other out, up and down, but you've got force tension in the x direction is going towards the right. There's no force to the left that's balancing it out, but we're told that the object is going at a constant speed. So there must be a force in this direction that's balancing out the force tension in the x. What could that force be called? That is a force friction. As the box is being moved at a constant speed to the right, friction will oppose it by moving it to the left. So what would be the sum of the force formulas here? Well, for the x direction, the sum of the forces is only 2. There's force friction plus force tension x. And since it's moving at a constant speed, that tells me equilibrium, or 0. In the y direction, the sum of the forces is equal to 3, actually. There's force normal plus force tension y plus force gravity, and that is equal to 0 as well, since the box is not accelerating up or down. Okay, now let's look at this situation. A box is moving at a constant speed on a frictionless surface. Okay, so the surface is frictionless. And something that is frictionless in real life, or practically frictionless, is dry ice. If you've ever played with dry ice on a tabletop, it moves across the tabletop with relative ease, meaning there's no friction between it. So we're going to pretend instead of a box, we're going to say that this is dry ice. So we have dry ice that's moving at a constant speed on a frictionless surface. What would be the force diagram? We've got force gravity that's pointing down. Then what's touching the dry ice? The table is touching the dry ice, and so it would exert a force normal going up. Is there anything else touching the box? No. And so this is the answer. Force normal and force gravity would cancel each other out. There are no x forces at all. So my y formula would just be force normal plus force gravity, and it's not accelerating up or down, so that it's equal to 0. So you can have something moving and not have any forces, such as this case right here. There are no x forces, and yet the object is moving. Remember, the forces are not necessarily dictating motion. The forces are dictating change in motion. If there's no forces there, the motion can't change, and that's why it's going at a constant speed. All right, final one right here. This is a box that's resting on an inclined ramp. This is probably the most difficult to picture, but we're going to walk you through it so you know how to do this. If I were to draw my force diagram of what's going on here, I have my force gravity is pointing down. I have my force normal that's going perpendicular away from the surface, such as this. And then the box wants to go down the ramp, so the force friction is going to oppose that motion. It's going to go diagonal up here. And I'm going to just, for this problem here, I'm going to draw the same force diagram actually on the picture so that you can see what's going on here. So force gravity is going straight down. Force normal has to go perpendicular away from the surface. And then force friction wants to oppose the motion. The block wants to move down the ramp, but the friction is opposing it. That's why it's facing up. Now, from this force diagram, you can see out of the three forces there, two of them are diagonal. Force friction and force normal. This is going to create a problem later on. So there is something that we can do that would make the problem easier. What you are allowed to do as the physicist is you are allowed to take your axis and you are allowed to rotate it to where your force friction and force normal are in line with the axis, and your force gravity is what's diagonal. The reason why you'd want to do this is actually several, but the primary reason right here is so that the force gravity is the only force that is actually needing to be split up. So when you do that, force gravity y will always be in line with the force normal. Force gravity x will always be parallel to your surface. So that's force gravity x, and this is force gravity y. Anytime you have a ramp problem, such as this, the x-axis always becomes what's in line with the ramp. The y-axis always becomes what's perpendicular to the ramp. Always. Finally, how would that work out when you are looking at the angle? Well, we know the angle right here of the ramp is 35 degrees. So in your force diagram, how do you know what the angle is? If the angle right here is 35 degrees, the angle right here is also 35 degrees. And I'm going to show you how you can get that geometrically. So I'm going to erase what's on the board already, and I'm going to redraw that force diagram so you can actually see how all of this works. So we've got the floor right here, and we're told that it makes 35 degrees. Now, we know that force gravity goes straight down, force normal goes up perpendicular, and then force friction goes along like this. Now, I'm going to draw in the force gravity in the y direction and force gravity in the x direction. Notice how force gravity y and x make a right angle with each other. Now, when I drew in the force gravity, what I did was I made a right triangle right here. And so if this is 35 degrees, this angle right here has to be 55 degrees, so that everything adds up in the triangle to be 180 degrees. Now, when I drew in my force gravity y, I made another right triangle. I made a right triangle right here. So right triangles are 90 degrees, and if of that 90 degrees, 55 of it is right here, then that means 35, the remaining, must be right there. This concludes the video on force diagrams.